All right, so this week we're going to finish up chapter 2, and starting off, we're going to do the properties of water. So, as you can see, make sure that you had finished your chapter 2 summary and Learn Smart and then submitted them so that you can get grades for them. And then today we are going to cover the salt and water hypotheses that you guys actually were supposed to finish up on Friday. And then we're going to do property of water notes. So the learning objective is still pretty much the same because it's covering this whole unit, right? So learners will be able to justify the selection of data regarding the types of molecules an animal, plant, or bacterium take in as building blocks or excrete, obviously, as waste. So for the mini investigation, remember, y'all were looking at when I did the demo for when you mix table salt, which is called NaCl chemically, with water, which is H2O as its chemical formula, versus when we mixed table salt with vegetable oil. And if you recall, I asked you to write a hypothesis, and the hypothesis should have been, if I mix table salt with water, then, for example, the table salt will dissolve, or the table salt will not dissolve, right? Same for the hypothesis for the table salt with the vegetable oil. And when we looked at the results, we actually saw that the table salt, for the same quantity of table salt poured into each solvent, right? The liquid, the water or the vegetable oil, the salt dissolved inside of the water, but it did not dissolve inside of the oil, okay? And from seeing that, and from talking about the structures of these, right? Because we know that NaCl is ionically bonded to each other. That means that the Na gave up an electron to the Cl, and therefore the Na is a positively charged atom, and the Cl is a negatively charged atom. And because they are positively and negatively charged, they are attracted to each other. So they stay together when they're in a solid state. Now, once you add in the water, though, the reason why the NaCl dissolves is because the water, remember, it is a polar covalent molecule, which means that on the oxygen side, because the electrons spend more time over there when they're shared, it's a little bit negative. And on the hydrogen side, the electrons spend a little less time over there. So they're a little positive. And so since water molecules have a dipole, right, they're polar, the slightly negative side pulls on the NAs of the salt. And the slightly positive sides of some of the water molecules pull on the Cls of the salt and pulls them apart. And upon breaking them apart, you break the solid NaCl into ions inside of the water, and ions are actually not visible by the naked eye. So that's why the salt is dissolving in the water and we can no longer see it. Now, on the other hand, we saw again, NaCl is ionic, right? Which means that it has charges. But when you put it into vegetable oil, it actually didn't dissolve. No matter how much I stirred it for the same or more amount of time than I stirred the salt in the water, and it still would not dissolve. You could see all of the crystals, and that's because vegetable oil is a non-polar covalent molecule, right? So the bonds inside of vegetable oil are non-polar, which means that the electrons in the shared bonds are being spread across two atoms equally, right? So no side is more negative and no side is more positive than the other. And since there are no charges, there's nothing to attract the oil and the NaCl to each other because nothing's going to pull on the positive Na and nothing's going to pull on the negative Cl because there's no charged parts of the vegetable oil molecules. And since they're not going to be able to pull the NaCl apart, the NaCl is still going to prefer to stick to each other, right? The positive Na and the negative Cl are going to stick to each other more strongly, and therefore they are going to stay in a solid state and not dissolve. Okay, so that's the logical reasoning behind the results. And the whole point of this mini investigation demo that we did was because like dissolves like. So things that have charges or things that have dipoles, right, mini charges, tend to like and be able to break apart other things that have dipoles or charges, right? So charges break apart things that have charges. And then things that don't have charges tend to break apart things that don't have charges, right? So vegetable oil would be better at breaking down a non-polar solid than it is at breaking down something that's ionic or polar, right? Because like dissolves like. You can already kind of tell that when you try to mix water and oil together, right? They don't mix because they don't associate with each other, right? They can't dissolve each other because water is polar covalent and oil is non-polar covalent. They can't even interact properly, okay? So again, this whole thing was set up to talk about like dissolves like, And that's just really, if you have charges, you'll probably be better at breaking things down that have charges. And if you don't have charges, you'll probably associate and break down things better that also don't have charges. Okay, so moving on. So water is polar. We just talked about that. It is a polar covalent molecule because the oxygen inside of the water molecule is very, very, very electronegative. And the hydrogens are not, which means that the oxygen pulls on the electrons a lot harder than the hydrogens, and therefore the sharing is unequal. That develops a dipole on the molecule with the positive side on the H side, and then the arrow side on the O side. Now, water has a high heat capacity. And let me explain this after I read out the definition. So 1 calorie is the amount of heat energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And this was a unit of measurement that humans created based on water because water is essential to life. Most other covalently bonded liquids only need half the amount of heat energy to increase 1 degree Celsius. So if you've ever boiled water before, you know it actually takes quite a long time when you're just waiting for it to boil on the pot and you're staring and waiting, right? But any other covalently bonded molecules like NO3 takes a lot less heat to add it to it in order to boil, right? And that's just because water has special properties of having hydrogen bonds. So hydrogen bonds greatly help water absorb heat without changing temperature. Okay. All high heat capacity means that it can contain a lot of heat before it changes forms, before it changes from ice to water and from water to gas. High heat capacity, right, can contain a lot of heat, right? Capacity is containing, and it contains a lot more than most other liquids of covalent bonding. It has a high heat of vaporization. So this is related to the last one. When you convert 1 gram of water to a gas, aka you're boiling it into a water vapor, it requires 540 calories because hydrogen bonds all must be broken before water can boil. So not only are the molecules just at a resting, like slowly moving state when they're in water, they're also attracted to each other really strongly from hydrogen bonds, right? The negative side of an O is attracted to the positive side of an H. And because they're not only not moving around very fast to become gas, they're also stuck kind of close to each other because they are attracted to each other. You have to break those bonds and then also give it the energy to move really fast as a gas molecule, and then it'll become a water vapor molecule, right? This gives animals an efficient cool down mechanism. This is also why coastal areas are temperate in the summer. So up here in North Texas, we don't really experience that because it's hot in the summer and it's kind of cold in the winter because there's no water bodies nearby to absorb the changes in heat and the changes in cold weather. So when I lived on the East Coast though, it doesn't really get that cold or that hot because we're right next to the ocean. And the ocean is a huge body of water, and therefore a lot of the heat generated is absorbed by the water, and the water still isn't really affected. Or a lot of the loss of heat is also not really affecting us on land because the water actually loses heat very slowly too. So it maintains its own constant state for a lot longer than most other liquids. Okay, so it takes a lot of energy to boil water, and that's kind of cool because like that's the reason why when dogs are panting and the water is evaporating off of their tongue, it's taking a lot of energy with it evaporating, and that energy is heat, so the animals can cool down when they pant. Water is a good solvent, right? We just talked about this in the demo. Because water is polar, it can dissolve many substances, especially those that are polar as well. There are some molecules that most of the bonds in them are non-polar, but then some of the few bonds built inside of their structure are polar. And then that means that water can pull it apart already, just because there is some part of it that's polar. Other molecules that are ionic, that are polar, are easily broken apart by water. So the term hydrophilic means water loving. So ions that have charges, right, positives and negatives, and polar molecules really, 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 really like water, because water has positive and negative charges. So they're attracted to each other. And so things that are hydrophilic will interact with water and will probably dissolve in water or mix with water. Now, on the other hand, we have hydrophobic, which means water fearing, right? When you have a phobia of something, you have a fear of it. So non-ionized, so things that don't have a positive and negative charge, and then also non-polar molecules for example, oils, do not mix or interact with water. Okay, over here, I have a kind of conversion thing for y'all because when we say calorie, you think about food, right? But on your food labels, it's actually not with a lowercase c, it's with a capital C. And so one lowercase calorie is only 1/1000th of the capital calorie that we usually refer to, right? So 1000 calories with a lowercase c equals one big C calorie. And this big C was just used to represent kilocalorie, but it's just easier to keep the word the same for like regular daily use. So they kept it and they just capitalized it instead. So we keep talking about like dissolves like. And again, so the Na, like we said, leaves an electron with the Cl. So it loses a negative charge. So the positives in the nucleus are no longer balanced. So it's more positive, right? So it's a positive charge. The Cl, since they gained the electron, now have an extra electron, which is an extra negative charge. So now their nucleus is no longer balanced and they are extra negative. So the water, because there is a negative charge side and a positive charge side because of the polar covalent bond and unequal sharing of the electrons spending more time on the O, the negative sides of the water are likely to attract to the positive side of Na because opposites attract. And when you have a lot of water molecules stuck to the Na, there's no surface, right? You could have 5 or 6 waters with the O's all stuck on the Na, and that leaves no room for the Cl to bond to it anymore, no matter if they're positive or negative. And on the other hand, if you have like 5 or 6 water molecules stuck on the Cl with the H's touching the Cl because the positive was attracted to this negative, then there's no room for the Na to bond to the Cl. And therefore the Na and the Cl are broken apart because there's water molecules surrounding them and separating them from each other. And that can only happen because water is polar covalent and because NaCl or salt is ionic. And again, like dissolves like, they both have charges. So here's a picture of what I was saying. So salt in the water is split into the Na positive ion and the Cl negative ion. Now, like I said, the O's are the negative side of the water molecule. So they are going to be the ones that are attracted and touching the Na or the positive part of the salt. On the other hand, with the H's being more positive, they're the ones that are going to be more attracted to the Cl or the negative ion in salt. And as you can see, once they are fully like pulled apart and covered by the water molecules, these salt ions can no longer come in contact with each other, and therefore they become invisible to the naked eye, right? So this is my drawing, but this is the actual diagram of what they look like. Cohesion is a term that we use that means the ability of water molecules to cling to each other. So because water molecules are polar covalent molecules, they have a positive and negative charge on each molecule, which means that they're not only attracted to salt, they are also attracted to each other because the H's have positives and the O's have negatives. So the O's of one molecule will be attracted to the H of another molecule. And then the H of one molecule will be attracted to the O of a different molecule. So they're all attracted to each other, and that is called cohesion. Adhesion is the ability of water molecules to cling to other polar surfaces. So remember again, the negative part or the O of the water will stick to any positive surface, and the H's will stick to any negative surface because the H's are positive and they'll be attracted to negatives, right? So the surface tension demo that we usually do in person is when you have a penny and you drip droplets of water onto there. Last year, the maximum number one of my students got was 48 droplets of water from a dropper, like one of those little clear plastic pipettes, onto a penny without it bursting or overflowing. And the only reason that can happen is because the water is attracted to the surface of the penny from adhesion, and then the water is also attracted to each other for cohesion. Now, this top surface has water tension, and water tension is pure cohesion. It is water sticking to water. It's the same reason why bugs and small like spiders and some lizards can walk on the surface of water. It's because they're so light that they're supported by the hydrogen bonds that are on the surface of the water holding the water molecules together. So they're that light or evenly spreading their force along the surface of the water that the hydrogen bonds are actually strong enough to hold them up. So density of water is kind of weird too. So if you ever put ice into a cup of water, the ice actually floats, right? Because ice is less dense than water. Water is actually the densest at 4 degrees. So that's right before it freezes. So when frozen water molecules form a lattice is kind of like a crystal structure where they're in a set point distance away from each other, and their distance to another water molecule is always the same distance away. So it's kind of like when you build a 3D, like if you build a cube or if you build a tetrahedron, right? So they all have like a specific distance between each point, and each point in that shape is, for example, a water molecule. And when you have them frozen, they no longer move around, and the hydrogen bonds no longer pull them close to each other. So they're actually spread further apart than they would be when they're in water. Because when they're water, they're free floating. They're also attracted to each other once in a while, bouncing off of each other by hydrogen bonds. So they're actually closer together when they're liquid than when they're solid, which is the opposite for most chemicals and most molecules that exist. So it's kind of important though, because in real life, when you think about it, in a pond, when it freezes over in the winter, if ice was actually more dense than water, then the ice would start forming and then fall to the bottom of the ocean and drag all life with it and drown everything that needed air to breathe, right? So it's actually beneficial to things in nature that ice is less dense than water and it floats on top. So at the most dense side of this spectrum, we have liquid water. And then we have solids in the middle, right, because it floats in the liquid. And then we have the least dense, which is gas, because gas molecules have so much energy and they're bouncing all over the place, right? And so they're always really far apart from each other, right? Most things, their solid is the most dense, and it would sink in the liquid form of the same chemical. And the liquid is the medium side of the spectrum, and then the gas is still the least dense. So water is kind of special because the liquid and the solid version of them are flipped compared to most other chemicals and molecules when you compare who is more dense. So to close out this lesson, I'm going to have you answer this essay prompt. So I want you to explain how the properties of water enable transpiration to occur in plants. In your essay, you must define transpiration, hydrogen bonding, adhesion, cohesion, and evaporation. So you may look up the definitions when you need to if you don't already know them, but please make sure to paraphrase them into your own word because the plagiarism checker on Google is actually pretty strict. So I'm gonna have you get started right after you finish this note taking and after you turn in your notes for your extra credit. And you're going to turn this in as a formal essay and it's gonna be due by the end of the calendar day. So again, I want you to consider what hydrogen bonds are. Remember, it's the attraction between molecules. You want to think about the reason why water molecules are attracted to each other. You want to think about the xylem, which is the tube where water moves up in plants, and the phloem where sugar and food moves down, right? The internal structures of plants. Transpiration is the process by which plants lose water through their leaves when the water is getting pulled up through the leaves and evaporating. So it happens when it's really, really hot, and it's sometimes bad for the plant if you think about wilting and stuff. The outline that I think is best for y'all to follow when you're writing this essay is to kind of define transpiration, define polar covalent bonds, hydrogen bondings resulting from polar covalent bonds, then talk about what adhesion is, cohesion is, how the xylem structure is important to transpiration because of what is moving through it, aka water, what evaporation is, and then what transpiration is as a process that like makes use of all of these other terms. So again, that's the structure that makes the most sense to follow. If you come up with your own structure and it makes sense to you, that's totally fine as well. But again, this is due at the end of class today.